The title of my talk is Practical Collaboration for IoT Security. And just to unpick this, there's three sort of like key dimensions to what I'm talking about at the moment. So everything I'm going to talk about is under the umbrella of the ManySecured project. And firstly, to emphasize what we are doing here complements some of the existing sort of IoTSF requirements work, is it's much lower level. It's very, very concrete and engineering based. And as such, some of the things that I'm going to talk about in a minute are going to skirt on the surface of some quite detailed technical initiatives. The second dimension is the focus. So the focus is unapologetically on the gateway, or the IoT gateway, and I'll say a little bit more about what that means in a minute. And then the third subject I want to tease apart is the issue of collaboration. And there's two parts to that. There's how do we collaborate to develop the tech, and then how is the tech used in a collaborative fashion. So just focusing on the first bit first. So just a little bit of history. ManySecured started as a collaborative project. It was kindly funded by Innovate UK, and its initial sort of seed partners are ourselves, Inquiry Minds, the IoT Security Foundation, University of Oxford, and Cisco. But I'm pleased to tell you that sort of like already, with almost sort of zero marketing and recruitment, we have 24 active organizations who are part of the ManySecured SIG activity and are helping develop it going forward. That's the first part of the collaboration. So now let me unpick the gateway. So I'm going to very, very quickly just remind some of you, but maybe introduce some of you to some other points of why the gateway we believe is so important. So firstly, it's eminently pragmatic. There are millions of compromised IoT endpoint devices that have already been released. I mean, you can pick your own sensationalized figures of various news feeds, but it's quite clear it is a manifest issue. And I also advise you to very carefully listen to Jan Getzima's presentation that's to follow, that's going to focus on one part of ManySecured that says not only are there lots of compromised devices out there, there are some, if you listen to what he says carefully, clearly some systemic design weaknesses that impact almost all current routers and IoT devices already out there. And any new IoT endpoint technology, whether it comes from a new standards body or a new set of requirements, is going to take literally decades to churn to the market. So pragmatically, we need a defense that we can implement, and obviously the gateway is the best place to do that. But there's a visionary aspect to this. I think gateways are evolving rapidly. And they have enormous potential, not just for security. And essentially, if you think about it carefully, a gateway, a router, is essentially a server in your own home, especially in the consumer context. And there's not many devices that satisfy that characteristic. As such, it's an interesting sort of opportunity for future developments. And then I'm going to go to the core of it, which is essentially what I call the triple threat. Firstly, it is just a fact. Routers are one of the principal attack targets. And I've shown you this before, but I'm in a recent sort of like semantic presentation analysis, just 75% of infected IoT devices essentially are routers. But obviously that has a knock-on effect, because if it's an attack target, it then also becomes an attack vector, because once you compromise the router, especially for access to DNS, you have almost unlimited ability to create mischief. And then the third sort of like key factor of the gateway focus is, you sort of hope the gateway is your line of defense. It's certainly the principal line of defense for external attacks coming in sort of like IP through the modem, but also, depending how the router is configured, it has a reasonable level of protection against internal attacks. Therefore, if the router is compromised, your defense is compromised. So that constitutes three really quite compelling reasons why we need to consider the gateway quite carefully. But then, just additionally to that, these gateways are complicated. We use the word gateway quite deliberately because it's quite a knotty topic. Because basically what we're saying is gateway is anywhere one set of traffic is being sort of like marshaled into another set of traffic. So in a typical consumer deployment, you've got the modem that's sitting on the border between the open internet and your internal network. But then internally, you might have repeaters whether they be Wi-Fi boosters or power lines, sort of like systems which are routers in their own right. And then, practically go down Currys or buy off Amazon, an IoT system. Often there will be an IoT router gateway, whether it be a Philips Hue, an Echo or SmartThings, and they're interestingly acting as gateways between two very, very different types of network. And then finally, gateways or secure gateways should be smart. I mean, just using the very crude, castle analogy, look at the defenses on the castle. I mean, the walls on the outside are relatively dumb. I mean, they're big, they're thick, they're defensive, and they're dumb. You need the intelligence at the gateway, at the portcullis, because that's where you're opening, shutting the drawbridge, and that's where you need someone smart to know who you should let in and who you shouldn't let in. So that's very much why we're focusing on the gateway, and certainly the intelligence within the gateway. So, to those of you that have heard some of the ManySecured presentations before, the scope slides have been evolving slightly, and that's a healthy thing, because we're trying to clearly and crisply identify what are the unique components that we're developing. And essentially where it sits now is there are 5 distinct activities running under ManySecured. So the first is the GCert, which is essentially evolving some of the certification and assurance activities, but looking at addressing the gateway element itself. So on the basis it's a risk, then we should defend that risk, and we should defend that risk with best practice. And Ian Poyner will be talking specifically on that issue a little later on, about, I think, 11:15 if we stay to plan. The second element is the SUIB, the secure usable sort of internet browser, which is essentially look at the onboarding issue, which is a lot more complicated than you think. And even actually just accessing and configuring an IoT device on an internal network is very slippy and tricky concept. Jan's going to be talking about that immediately after my talk about 10:10. And then in this talk, I'm going to focus on the other 3 elements, which I've just stripped down on this slide. And essentially, it's 3 bits. It's NetMon, which is essentially a mechanism of doing network control. NetCon, which is a mechanism of doing network control, and something that we're calling D3, or distributed device descriptors. So 3 very simple components or enablers. They sit on top of the router or within the router. So NetMon and NetCon very specifically are proposed interfaces that a router would support. And D3, and we'll dig into this in a minute, is essentially an abstract language or an abstract set of statements that essentially provides us intelligence, a higher level language with which we can start describing our problems. And we've designed this way because when you're doing any form of collaborative sort of like engineering, whether it be open source or standards, there's an art to it, and the art is identifying which are the bits that people are prepared to collaborate on, and therefore it's non-differentiating, but there's economies of scale if everyone sort of like collaborate on those issues, and which are the issues where people will naturally want to differentiate. And in this slide here, you'll see the security agent local, the security agent cloud. That's where a lot of the smarts will reside, and what will realistically be a differentiating smart intelligence for a number of different organizations going forward. And the NetMon, the NetCon, the D3 have been designed to be secure, interoperable interfaces to directly support that innovation, so that they don't contradict it, they don't compete with it, but they do, or the intention is they make it more scalable and allow us to deploy some of these smarter, intelligent sort of like security interventions at scale. That is the clear aim of what we're trying to do. And so in the rest of this presentation, I'm going to start digging into some of the details of these and explain exactly what it is we're doing, and exactly sort of like how far we've got so far and where we still have to go. So firstly, NetMon. So what is NetMon? So if you are going to implement any static or sort of dynamic security mitigation that's going to monitor what's going on your network, you need a method of accessing the security pertinent metadata coming off that device. And we've set ourselves some quite ambitious targets. We want this component to be accessible from the cloud in a secure way, because we assume that some deployments will require the assistance of cloud-based agents, ISPs, security consultants, to be able to help them sort of like analyze and protect their network. But also we want it to be accessible from the local network. So whether it be that the router itself, adjacent to physical routers or components, or even mobile applications. And that's quite a tall ask, actually, getting that working properly. And it actually digs into some of the issues that Jan will talk on later on. Is okay, fundamentally, whether it's IoT or non-IoT, how do we make a secure connection over HTTP on an internal network? And I think that will form part of the solution. I know the second part of the issue of what we're trying to deal with Net1 is we're trying to define a real-time stream of security pertinent metadata, and fundamentally we have a challenge that we're trying to address here, in that on the one hand, the data needs to be detailed enough to be able to analyze and pick up interesting security signatures. But on the other hand, it's got to be performant at scale, because this is technology we're hoping to deploy in many routers. Therefore, it has to be scalable. So there's a tricky sort of trade-off piece of analysis that we need to do to make that work. And then the third part of it is although the initial prototypes that we're developing in the specs are focusing ostensibly on what we call the classic IP networks, we want the core technology to be extendable to the non-IP networks. So the Z-Wave gateways, the LoRa gateways, the proprietary industrial controllers. If we get the definition of the abstract Net1 interface correct, that gives you the ability to protect the network in the round, sort of like the heterogeneous, sort of like interconnected real-world network that sits inside your home, rather than just the IP bit that it sits on the router. And in terms of how, I won't go into too much detail now in terms of how we're approaching it, but that detail is available in the working group. But we're essentially trying to build on best practice we find elsewhere, strong sort of like PKI-based security, gRPC, which is a highly optimized remote procedure call structures for networking traffic, as well as essentially building up on sort of like PCAP structures and SQL structures for the actual network access. So we have an emerging set of sort of like prototypes that are being developed, as well as standards which are addressing those high level requirements which are summarized in that slide. Now the inverse of that is NetCon. So if Mon is monitor, Con is control. So Mon is the sensor system, the Con is the actuator system. One lets us see what's going on, the other lets us do something about it. And fundamentally, it has very similar sort of like high-level requirements to the Net1. We want it to be accessible locally, and we want it to be accessible from the cloud. We need it to be highly secure. But then, in terms of how it actually works, and we're still playing with the different ways we can do this. But essentially, what it comes down to is there's two coarse-grained methods of controlling the network. One is creating sort of subnets or virtual sort of like subnetworks, which essentially contain traffic. So it stops things coming in and it stops things coming out. Now this is a subnet, so this is below the internal IP level you're connected to. And that actually offers you, quite a lot of leverage in terms of how you control something, because if something's suspicious, you quarantine it and you put it on a subnet with much limited privileges. But then there's a more specific method that we can also use, which are essentially almost like device-specific firewalls. So this is where you look at an individual device, and based upon its declared or inferred qualities, you say you can only do this. So they're both sort of very similar techniques, whereas one method is device specific, the other is essentially, the subnet is essentially a cluster of devices which are all sort of like obeying the same rules. And again, we're using a similar set of primitives to sort of like building the protocols, building on the security methods that we're developing. But in terms of our actual implementation and tests, we're actively targeting sort of like the OpenWRT sort of like community and open source platform, because that is the route to sort of scale. And so, bring it together. What have you got? You've essentially got an intelligent control loop, and that's what we're trying to develop here. We're trying to create the environment where we can implement an infinity of smart functions to intelligently monitor and control what happens on your network, to both reduce the probability of external attack, but also to reduce the probability of internally pre-exploited devices, attacking your network. So it has a full visibility of what's going on and a method of controlling it. And so a few comments on this, which are sort of like key to why it's designed the way it is designed. So the MON can be, active, intercept, or passive. So you can implement it on top of an existing router function inside the heart of a router, but you can also implement it as a network tap. So that's a passive network monitoring device. So what that means also is the NetMon and the NetCon can be implemented on separate physical devices. So again, as with many sort of like collaborative initiatives, we're trying not to be too restrictive in terms of how this stuff is deployed and how this is implemented, because we need to give people scope for innovation. But we're trying to define the methods and the protocols such that they're clean, as simple as possible, and can be implemented in one of n number of ways. And we've also already got evidence that that's doable. And then, as I said earlier, although we're focusing principally on the IP networks, the concept of NetMon and NetCon can be implemented on a SCADA network, on a LoRa network. We just need to get the abstractions of the definition of activity and device rights. And why are we doing this? Why are we doing this? I mean, as John pointed out earlier on, I've been doing AI for quite a long time. There's lots of products on the market at the moment that offer, smart AI-based network security or even IoT-based security. But as someone who's relatively experienced in the art, I can tell you the one fundamental challenge you have is access to data. And unless we can commoditize that, unless we can commoditize access to the underlying sort of network activity, you'll never really achieve the smarter intelligence and smarter controls that is a clear and obvious sort of ambition almost industry-wide. So consider these drivers. The standard computer architecture is a driver that almost hides the implementation complexity of the underlying network and the underlying physical piece of hardware, and provides a functional interface for you to build at scale. So that's sort of like the NetMon and NetCon on their own. And we've just had I've called it smarts. I've called it the smart intelligent functions in the gray, because that's out of scope but place for innovation. But what we can do is and I think we will demonstrate in a minute, there's a clear need and a clear evidence that we need to have a collaborative infrastructure or collaborative language to be able to help the smarts talk to each other. I mean, very simply, a threat, if identified on a device, it is clearly in everyone's interest to be able to share that. But in order to share that, you need a language to do so. So D3, or distributed device descriptors, as we're calling them, is essentially a language which is essential for intelligent collaboration. It helps us address the problems of what did you see, and to some extent, what are you going to do? Now, I'm going to skim in a minute on and give you a flavor of what D3s look like, but we've identified, I think, currently about 15 distinct use cases that these D3 systems can support. And I won't talk about them all now, but I'll just give you a quick sort of headline. And I think the first observation I would make is if you look at, say, the ETSI best practices, you can almost unpick every one of those 13 recommendations and come up with a clear and compelling reason of how these distributed device descriptors can at least help, and in some senses, and almost essential to actually to deliver that vision at scale. So I'll pick up a few very quickly. So the first use case, obviously, is assert a type, right? Be able to say this type exists, this webcam from this manufacturer of this model number exists. And so that's the first use case. The second use case is what we call the recognition use case. So the recognition use case is, I see a device, it's a physical instance of a device, and I think it's of type X. So recognition really provides a mapping between a device you see on the network and a type which has been declared as use case 2, use case 1. The third use case that I'll talk about is the standard security concept of least privilege. So again, common sense, I've bought a webcam. This webcam, we know in advance, whether the manufacturer tells you or someone else tells you, should only really communicate on these port numbers over these IP addresses. We have a strong pre-knowledge of what this thing should we do. And therefore we can create a language using the D3 system to explicitly describe what that sort of whitelist activity should be. And then that maps again back to the assertion. And then I'll just flip to two others because I think they both feature quite strongly in most sort of like IoT requirement recommendations. Vulnerability disclosure. So I'll talk in a minute about how sort of like D3 can complement that ambition of making vulnerability disclosure an active security defense. And then another one, update method, keeping devices updated. You know, if you want to keep your IoT device updated, it helps enormously if you know what devices are on your network and what type they are, and then also what firmware they can be updated with. And so we've designed D3 in a particular way. So the first D in D3 is distributed. Now, to those who are familiar with it, it shares a lot of basics with the IETF MUD specification, the manufacturer usage description, and certainly it's informed some of our initial thoughting. But it goes much further than MUD in two ways. One, we're addressing a wider number of use cases. Two, fundamentally, in the D3 model, we don't always assume the manufacturer is the optimum source of truth. And there are many very practical reasons why that would be the case. Firstly, they're not always there. That they might have sort of gone under. You know, basically products last longer than companies, especially in a high velocity market like this. But also, we've tried to define the D3 system such that it will work on legacy systems. We don't want to insist that every manufacturer produces the type descriptor and the behavior descriptor and embeds it in the device before it's useful. We've designed it in a way that it can be post-fixed, added on to sort of like existing legacy systems. And there's other sort of like design requirements sort of like in there that have helped inform the way it's evolving. But it's fundamentally, when it comes down to it, that is the key differentiator. It's the distributed nature of it and the fact that these information sources can come from many forms. I don't know, what is it? It's actually quite simple under the hood. It consists of a set of attributes that say, this is the device, this is the originating manufacturer, this is the model number, and here's a usable link where you can click on and see something about it. The most important thing probably from a security perspective is these behavior descriptors, which are very similar to the MUD type descriptors, which essentially is a least privileged statement of what we expect this device to be doing. And then we've got sort of, just as an exemplar, I'm showing how these device descriptors can be interlinked with a firmware sort of descriptors, because clearly if you want to use the update method or even describe something, that's key. So probably to make this clear, the easiest thing to do is to give you a very concrete use case. So this diagram shows you three different types of descriptor here. So if you see in the green and yellow here, so in the green and yellow, you've got the type assertions. So this is webcam type A, this is speaker type B, this is bulb type C. But obviously, I've just used a shortened version here. And the key point about this, again, this type assertion can come from different sources. Where the manufacturer wants to make its own type assertion, they essentially sign that statement. All of these D3 statements are signed, cryptographically signed statements. So we know we have an authority, like where the source comes from, and then we have a piece of information. But you know, we've anticipated in the system the ability for these types to be crowdsourced, as well as to be produced by an intermediary. So these organizations that may or may not be the manufacturer. The D3 statements on the left are the recognition statements. And so these are the mechanisms via which an individual device is tied to a type. And again, these bindings can come from different sources. The user might physically install a device, right? In which case they might sign the fact that this device with this MAC address is of type X. We might have an intelligent agent, smart IA agent, that can make this inference based upon behavior that it sees. So it's still a binding, it's still a recognition event, but it's coming from a different entity. And then the third one is there are obviously existing sort of cryptographic methods or soft methods. For example, FIDO and Matter both support a form of device attestation, which can also give meaningful information. So here we've got a device. We've bound it to a type, or we've inferred that it's of a type. And then because of the behavioral descriptions, we also have a well-known understanding, at least a privileged description of what that device should do. And if we have that, then when we dovetail that with Netmon, we have an optimal system for being able to dynamically protect your internal IoT. You've got your devices, you know, or you think you know what it is, you know what it should be doing, and then Netmon tells us live what it is really doing. So where A is out of the bounds of B, so where our Netmon feed is outside of the bounds of the behavior, then we can trigger to do something. And that could be anything from email and tell the user to do something, notify like the ISP or the device manufacturer that it's out of bounds, or using the netcon system, we can quarantine. So this is a very concrete way where we build on each of the individual elements to implement this dynamic control system. And secondly, just very briefly, vulnerability disclosure. So this is really, really simple one. I've just picked an arbitrary vulnerability disclosure method off the internet relating to devices. Here's the issue. At the moment, almost every vulnerability disclosure system has a free text form for vendor name and product number. The obvious opportunity here using this type of innovation is to replace this with a deterministic device type ID. It means that everything's much less ambiguous, and we can then use that downstream activity a lot more effectively. So finally, just to sort of like sum up where we are, this is evolving work. I've talked about 5 different areas, some of it sort of like more mature than others. Jan and Ian will talk about SUIB and GCERT in a moment, but the philosophy we're running is this almost like the internet standard, rough consensus of running code. We're implementing things first and then continuously iterating our specifications to update that. We've got a growing community of 24 organizations, and that's just natural. There's no active recruitment at the moment. Hopefully that will change over the next few months as we scale up. Our planned release, our specification release, is coming up end of November, and that will give the sort of like first draft specs of all of the components that I talked about, as well as a working sort of D3 portal, which is the concrete method by which you can start making some of these descriptions and tests. And in terms of opportunity for engagement, I mean, we've got 3 main areas. One, testing. So we do have devices now that implement the concepts that we're talking about, and we're very keen to evaluate that both from a consumer, enterprise, and industrial context. Obviously, as the other SIG members are doing at the moment, you can engage in the specification work by joining the SIG. And finally, there's an active sort of like development piece of work going on behind the scenes, which again, we are quite welcoming sort of like contributions.